June 12, 1925, Standard Oil's Bayway Refinery, Linden, New Jersey. A maintenance foreman named Carl Hendricks watched sulfuric acid eat through a 6-inch gate valve in the alkylation unit. The valve had been installed 3 weeks earlier. Carbon steel, same as always. Now the metal around the seat looked like Swiss cheese, pitted and corroded, green crystals of iron sulfate blooming across the surface. Hendricks knew what came next. Shut down the unit, drain the acid, replace the valve, restart. Cost per shutdown, $50,000. Time lost, 16 hours minimum. And in another 3 weeks, maybe 4 if they were lucky, the same valve would fail again. This wasn't an isolated incident. Across America's rapidly expanding chemical industry, corrosion was destroying infrastructure faster than engineers could replace it. The war had ended 7 years earlier, but the chemical revolution it triggered showed no signs of slowing. Synthetic dyes, petroleum cracking catalysts, ammonia synthesis for fertilizers. Every process demanded increasingly aggressive chemicals, sulfuric acid concentrations that would strip flesh from bone, nitric acid hot enough to glow, chlorine gas that corroded everything it touched. The valves controlling these flows, cast from traditional materials like iron, steel, and bronze, dissolved like sugar cubes in coffee. European suppliers offered limited solutions. British and German manufacturers had begun experimenting with chromium-bearing steels, but production remained small, expensive, and unable to meet American demand. Importing specialty valves meant delays, customs complications, and dependence on foreign technology. American valve makers, meanwhile, focused on volume production of conventional materials. Nobody had solved the fundamental problem of casting corrosion-resistant alloys into the complex shapes valves required. While Bayway's engineers were calculating replacement costs that would exceed $2 million annually, a Chicago valve manufacturer had quietly mastered something metallurgists considered nearly impossible. That company was about to discover that their expertise in casting exotic alloys would save an industry eating itself alive. Richard Teller Crane was born February 15, 1832, in Paterson, New Jersey. At 16, he apprenticed as a pattern maker, learning to carve wooden forms from which metal castings would be made. The work demanded precision. A pattern off by a 1/16 of an inch meant a casting that wouldn't fit, couldn't seal, served no purpose. In 1855, Crane moved to Chicago with $600 and a conviction that the city's explosive growth would demand brass fittings for plumbing and steam heating. He founded R.T. Crane Brass Works in a small workshop on Canal Street. The timing proved prescient. Chicago's building boom through the 1860s and 1870s created insatiable demand for reliable valves and fittings. When elevators began lifting passengers in the city's first high-rises, they required steam-powered hydraulics operating at pressures that would burst conventional valves. Crane developed specialized gate valves and check valves that could handle 300 pounds per square inch without leaking. More critically, he understood that quality depended on controlling every manufacturing step. By 1870, Crane operated his own brass foundry, machine shops, and pattern shop. No reliance on outside suppliers. No compromise on materials. Civil War contracts had established Crane's manufacturing credibility. Naval vessels demanded bronze valves resistant to seawater corrosion, a challenge that forced the company into early metallurgical experimentation. Between 1906 and 1910, Crane developed proprietary nickel-bronze alloys for ship valve applications. The work required hiring trained metallurgists, an unusual expense for a valve manufacturer. Most competitors employed machinists who could follow drawings. Crane employed chemists who understood grain structure, phase diagrams, and alloy behavior at temperature extremes. This distinction would matter enormously 2 decades later. By 1890, Crane Company was America's largest valve manufacturer, producing everything from half-inch plumbing fittings to 30-inch industrial gate valves. The company shipped products across the Americas and into Europe, competing directly with British and German specialists. Richard Teller Crane died in 1912, having built a manufacturing empire from pattern-making skills and an obsession with vertical integration. When World War I severed supply chains from Germany, American industry discovered dangerous dependencies. Chemical plants producing munitions and poison gas required specialty valves. German manufacturers like Deutsche Bergwerks had dominated this market. British suppliers, overwhelmed by war production, couldn't fill American orders. Crane supplied naval vessels and power plants, but hadn't yet entered chemical service. The war ended before American chemical infrastructure fully developed, but the post-war boom continued. Synthetic fertilizers, rayon production, and petroleum refining all demanded corrosion-resistant equipment. Then, in 1913, metallurgist Harry Brearley in Sheffield, England, discovered that adding chromium to steel created an alloy resistant to corrosion and staining. By 1925, stainless steel was available as rolled sheet and bar stock. But casting it into complex shapes like valve bodies presented problems that had defeated every foundry that attempted it. Chromium oxidized violently when molten. Carbon contamination destroyed corrosion resistance. Castings cracked during cooling. The rejection rate in early stainless steel casting attempts ran between 60 and 80%. No American foundry had mastered the process for intricate geometries. By 1926, America's chemical industry faced a crisis that seemed intractable. Plants were dissolving their own infrastructure, and nobody could cast the metal that would survive. Crane Company's foundry in Chicago faced what seemed impossible. Stainless steel contained 18% chromium and 8% nickel. When heated to melting temperature, 2,800 degrees Fahrenheit, the chromium reacted with oxygen in the air. The metal oxidized, lost its chromium, became worthless. Even when poured successfully, the castings cracked as they cooled. 60 out of every 100 attempts failed completely. But Crane had advantages competitors lacked. The company already operated foundries casting brass and bronze alloys. They employed metallurgists from Harvard and MIT who understood phase transformations and grain structure. And Crane had financial resources to fund expensive experiments. Annual revenue exceeded $50 million by 1925. The breakthrough came in stages between 1926 and 1928. Crane's metallurgists developed sealed electric arc furnaces filled with carbon monoxide gas. The gas prevented chromium from oxidizing during melting. They used ultra-pure raw materials to keep carbon content below 0.08%. Higher carbon destroyed corrosion resistance. They designed specialized molds with carefully placed risers that controlled how the metal solidified, preventing cracks. Machining the castings presented new problems. Stainless steel work-hardened rapidly, dulling cutting tools in minutes. Crane developed carbide tooling and slower cutting speeds. Production costs increased dramatically, but the alternative was plants shutting down weekly to replace corroded valves. By 1927, Crane was producing Type 304 stainless steel globe valves for sulfuric acid service. Initial output reached 50 valves per month. The price shocked customers. A 6-inch stainless valve cost 8 to 10 times more than its carbon steel equivalent. But at Standard Oil's Bayway refinery, installation tests revealed the economics. Carbon steel valves lasted 4 to 6 weeks in alkylation service. The stainless valves ran 18 months without detectable corrosion. At DuPont's ammonia synthesis plant in Bell, West Virginia, stainless valves operated 24 months in service that destroyed carbon steel in weeks. Plant managers performed calculations. Higher initial cost versus elimination of shutdown expenses. The numbers justified themselves immediately. Competitors attempted to replicate Crane's success. Most failed. Casting rejection rates remained above 50%. Crane's 18-month head start in a rapidly expanding market proved decisive. By 1929, the company controlled roughly 70% of America's stainless valve production. Patent applications filed between 1927 and 1928 protected key casting processes. Then October 1929 brought financial collapse. Chemical plant construction dropped 80% over the next 3 years. Crane's stainless valve sales plummeted. But the company's research and development continued. Engineers believed recovery would come eventually, and when it did, Crane would be ready. Meanwhile, they searched for new applications for stainless casting expertise. Petroleum refining provided the first alternative market. Catalytic cracking required temperatures above 1,000 degrees Fahrenheit and corrosive catalyst regeneration systems. Carbon steel failed rapidly under these conditions. Standard Oil, Shell, and Texaco adopted stainless valves throughout their cracking units. Unlike chemical plant construction, gasoline production continued through the Depression. Americans still needed to drive. The food and beverage industries discovered stainless steel's sanitary properties. Pasteurization and sterilization demanded equipment that wouldn't corrode, harbor bacteria, or contaminate products. Dairy processors, breweries, and bottling plants specified stainless valves. Coca-Cola and Anheuser-Busch became major customers. Consumer products proved more depression-resistant than heavy industrial chemicals. December 7, 1941, transformed American industrial capacity overnight. Within months, the government's synthetic rubber program demanded thousands of stainless valves. Japan's conquest of Malaya had severed 90% of natural rubber supplies. Synthetic production required butadiene and styrene plants operating with extremely corrosive catalysts. Crane's production jumped from 200 valves monthly in 1940 to over 2,000 by 1943. The company supplied 60% of all valves for government synthetic rubber facilities. Aviation fuel presented equally critical demands. High-octane gasoline for bombers and fighters required catalytic reforming using hydrofluoric acid. The acid dissolved carbon steel valve seats in hours. Every major American refinery, converting to 100-octane production, specified Crane stainless valves. German aviation fuel shortages stemmed partly from refinery corrosion problems their metallurgy couldn't solve. Then, in 1943, Crane received unusual contracts from the Manhattan Engineer District. The specifications demanded extraordinary precision. Nickel content above 8%, carbon below 0.06%, helium leak rates less than 10 to the -8th cubic centimeters per second. Every casting required X-ray inspection. Rejection rates had to stay below 1%, compared to 5 to 10% for commercial valves. The contracts specified 10,000 stainless steel valves, flanges, and fittings for Oak Ridge, Tennessee. The application remained classified. Crane engineers knew only that the valves would handle uranium hexafluoride gas, one of the most corrosive substances known. UF6 reacted violently with moisture and attacked most metals on contact. The K25 gaseous diffusion plant required zero-defect components. Foundry workers received security clearances. Quality control inspectors examined every valve under fluoroscopic equipment. At Hanford, Washington, plutonium production, facilities needed stainless valves for chemical separation cascades using nitric acid. The processes generated intense radiation, requiring remote operation and maintenance-free designs. Crane metallurgists worked on site, developing valves that could operate for years without human intervention. Nobody at Crane knew these valves were building atomic bombs until August 6, 1945. When World War II ended, Crane faced the classic defense contractor problem. How to convert wartime capacity, producing 18,000 valves monthly, back to peacetime markets? The answer arrived faster than anyone anticipated. The petrochemicals revolution exploded between 1946 and 1960. Plastics production, polyethylene, polystyrene, and PVC grew 400% in a single decade. Every process required corrosive catalysts, high pressures, and high temperatures. Stainless valves became essential throughout entire production chains. Pharmaceuticals discovered that antibiotics manufacturing demanded sterile, corrosion-resistant equipment. FDA regulations drove widespread stainless steel adoption. Pfizer, Merck, and Eli Lilly specified Crane sanitary valves for penicillin and streptomycin production. The Marshall Plan rebuilt European chemical plants using American equipment, opening international markets. By 1970, Crane operated manufacturing facilities in 35 countries. Nuclear power emerged in the 1950s as another application demanding extreme materials performance. Pressurized water reactors operated at temperatures and pressures that made ordinary water corrosive. The Shippingport and Dresden plants specified Crane nuclear-grade valves based partly on Manhattan Project experience. Only 4 manufacturers worldwide held nuclear qualifications. Crane was one. The metallurgical principles developed between 1926 and 1945 remained foundational. Chromium forms a passive oxide layer, nanometers thick, that self-heals when scratched. Nickel stabilizes the austenitic crystal. Structure, maintaining ductility and weldability. Simple chemistry, but execution required manufacturing expertise Crane had pioneered. Modern computer modeling refined casting processes, but basic techniques stayed unchanged. Richard Teller Crane died in 1912, never knowing his plumbing fixture company would enable the atomic bomb, save the chemical industry from corrosion, and launch the plastics age. He wanted to make reliable valves for Chicago's buildings. He succeeded beyond imagination. Return to Bayway Refinery, 1965. The same sulfuric acid alkylation unit. But the stainless steel valves installed in 1927 were still operating after 38 years. The plant that ate itself learned to digest nothing. And the company that solved it disappeared into infrastructure, invisible but essential. Exactly where the best engineering lives.